Good morning, dear students. We are discussing about nuclear magnetic resonance spectroscopy. And in nuclear magnetic resonance spectroscopy, in the previous class, we were discussing about the chemical exchange or proton exchange. Actually, proton exchange and chemical exchange, even though it is a tool to understand certain exchange reactions, but it induces some complexity in NMR spectrum. That's what we are discussing today. The complexity in NMR spectrum, and how do we resolve this complexity in NMR spectrum? How do we simplify the problems which lead to the complexity in NMR spectrum? So we remember that the chemical shift, by analyzing many organic compounds, we came to a conclusion that a certain functional group appear in certain region. So if you take the alcohol, it appears in this region, whereas a nitrogen compound, it could be amine, it could be primary, secondary, or tertiary, uh, it appears in this region. So suppose if you have a compound which contain an alcoholic group and a amine or secondary or primary or tertiary amine group, then what will happen? The peak of the alcohol as well as the peak of the amine may be merged. If it is getting merged, the information will be buried. You can't get the correct information. So this aspect is one of the complexity that we are facing when we are when we are analyzing the compound by using NMR spectra. So this is one of the example for complicating the NMR spectra. So let's see what are the factors that will increase the complexity in NMR spectra. How do proton NMR spectrum becomes complex? Just like I just said, the alcoholic proton and the amine proton, they may get overlapped. So when the signals overlap, useful informations are often buried. And proton exchange, what will happen? You are supposed to get the peak, a single peak, it may become two or it may become a broad end. We have discussed in the previous class. Then hydrogen bonding. Sometimes what will happen? The hydrogen bonding will be stronger, so the peak will not be appearing in the place where we are expecting. So again, it may lead to overlapping, or again it may lead to some complexities. When the coupling constant is comparable with the chemical shift difference of the coupled proton. So we have two important parameters in NMR spectra. One is in the chemical shift. So the position of the chemical shift, how many ppm, that value will tell you which functional group, the proton what we are observing could be the part of which functional group. And another information observation what we make in NMR spectra is splitting pattern. So what will happen is the coupling constant, suppose a peak would have split like this. This is coupling constant. Whereas what can happen is in another in the same spectra, the chemical shift would have appeared like this. So the chemical shift is different and the coupling constant is different. If both are having comparable distance, you can't make out whether it is a coupling constant or it is a the chemical shift. So what do we do? That is again another scenario where the NMR spectra is becoming complex. Another possibility is solvent effect. So sometime the organic compound what you have taken will have an identical proton to the proton which is there in the solvent. So it is a difficult issue. So how do you understand whether the peak appeared in the NMR spectra is due to the solvent or the organic compound? Here we use a simple technique. What is that is? In the solvent, we won't take normal proton. We only take the deuterated proton. Deuterated proton will not be recorded. So that's the simple idea. So these are the factors that makes an NMR spectrum complex. So the spectroscopy, there are a few tricks which we use to simplify the complex NMR spectrum. Let us look into that. The first technique, it is deuterium labeling and exchange. So what do we do is, like I just said, if you wanted to come out of the spectrum overlapping of the solvent compound and the compound which you are analyzing, you need to go for replacing the proton in the solvent by using deuterium or the deuterium. So what is the idea behind that is the deuterium 2H, the H2, it's the 2 is a superscript, actually D, or deuterium, the heavy isotope of hydrogen, has been used extensively in proton NMR spectroscopy for two reasons. The first reason is it is easily introduced into a molecule, and the second reason is the presence of the deuterium in a molecule is not detected by the proton NMR spectrum. So it is easy to introduce. The other one is the deuterated proton will not be understood by the NMR spectrum. So why it is not understood? Deuterium has much small magnetic dipole moment than hydrogen, and therefore it absorbs at different field strength. Although it broadens the peak of the neighboring proton, it does not split. And please understand, deuterated proton will not split it because it couples only slightly with the protons. So you must be remembering the basics. What are the reason for coupling? When deuterium replaces the methyl hydrogen in ethyl bromide, let us see what is going to happen. The technique is like this. Note that the multiplicity of the CH2 peaks changes from a quartet. Actually, if you take the CH2 CH3, the splitting of this is due to this. So initially, according to the rule, that is 3 plus 1, n plus 1 rule, so a quartet will be there. So what are we going to do? If you introduce a deuterium over here, it will become a triplet. If you introduce one more deuterium, it will become a doublet. If you introduce one more deuterium, it will become a singlet, as the hydrogens on the CH3 groups are replaced by deuterium. So this is how we solve. This is one technique. In BrCH2 CD3 means like when all the methyl protons are deuterated, no splitting occurs between the remaining hydrogens and the neighboring methyl, which is now completely deuterated. So there will be a single peak. Splitting will not happen. The same could be applied. Carboxylic acid and aldehyde protons appear between 12 and 9. This is the another next point. So acidic compound can be, in this case, what could be done? Acidic compound can be differentiated from aldehyde because the protons attached to the heteroatom exchanges readily with the D2O. So there is some complexity where what happens is like it appears in 12 parts per million or the 9 parts per million. So if you wanted to remove that particular proton, you can go for deuteration. So deuterium labeling technique is a good technique which simplify the complex spectra. And again, the active hydrogen atom of hydroxylamine group may be removed by shaking the solution of the compound in deuterated chloroform with heavy water and then separating the aqueous layer. The signal due to the hydroxyl and amino group would have disappeared when the spectrum was recorded again. Hence, any coupling between the hydroxyl and amino group and another hydrogen atom would also have been removed as a result of deuteration of this group. So, deuterium labeling technique will resolve the splitting pattern. So, you can change the splitting pattern, and the splitting pattern, like if you go comparing with the unsplit pattern, you can easily understand what is the exact spectra of the concerned compound. Another method is double resonance. So, the coupling between neighboring nuclei gives splitting patterns, and their analysis is useful for the structure determination of the compound. In some situation, however, these patterns are so complex that simplification of the spectra is desirable, and spin decoupling provides one such technique. So, we have discussed that there are four parameters that will give you correct information about the NMR spectra. By those things you have to use when you analyze the NMR spectra. Out of that, one is the splitting pattern, coupling constant, and all those things. So, what the splitting pattern, if you can make some changes, that's what we have done in deuterium technique also. This one more technique that will change the splitting pattern is a double resonance. So, the example of the proton NMR spectrum of ethanol serves as a good example, where the spin-spin splitting of the methyl signal by the methylene proton is due to three possible spin state. So, here in the previous example I was talking about the CH3, here what I am taking CH2, then when it is CH2 there are three possible spin state. So, it will be splitting the adjacent proton, whatever be the number, into 3, because n plus 1 rule, 3 spin states are possible. So, what do we do? Instead of having 3 states, if it is only having one state, the splitting of the CH3 will not happen into 3. It will be a single peak. So, if you do, this is the technique, if you irradiate strongly the methylene proton with an additional radio frequency at their resonance position, the methylene proton will get induced to change their spin state very rapidly. So, when they are rapidly changing, the NMR cannot identify each spin state separately. Instead of that, what will happen? The methylene proton will therefore only see the methylene proton will therefore only see an average CH2 state, cannot recognize that 3 spin state. It will be an average spin state as a single spin state, and coupling will disappear. Consequently, the methylene absorption will be eliminated, and methyl signal will be recorded at its usual frequency only as singlet. So, the idea that maybe the method is different in deuterium, and this one almost the same method it works out. And the another one which is very important, many times it was appeared in the question papers and all, is using a shift reagent. So, shift reagent, the chemical shift reagents are the organic complexes of the paramagnetic rare earth metals from the lanthanide series. Of the lanthanide, the most reputed one is europium, is probably the most commonly used metal. Two of its widely used complexes are tris dipavalo-methanato europium and tris 6677888 heptafluoro-2,2-dimethyl 3,5-octane diionato europium. Frequently, these two compounds, these two metal complexes are abbreviated EUDPM thrice. The 3 is upper side. Sorry, the 3 is bottom side, like it is supposed to be here. Here also. Europium FOD 3 respectively. So, the structure could be seen, it is like this. These structures are very important. You need to draw and learn it. Then, when such metal complexes are added to the compound whose spectrum is being determined, there is a profound shift in the various group of proton. What will happen? The proton, if it is supposed to be at 3, it may get a value less than 3, or it may get a value more than 3. So, what will happen? The proton peak will be shifted. Why it is shifted? Because we were using some particular reagent. So, that's why the reagent has got shift reagent name. The direction of the shift, it could be upfield or downfield, depends primarily on which metal is being used. Complexes of europium, erbium, thulium, and ytterbium shift the resonance to the lower field, while the complexes of cerium, praseodymium, neodymium, samarium, terbium, and holmium generally shift the resonance to the higher field. This lanthanide complexes, how the shifting is happening, what is the mechanism behind the shifting, if you ask. These lanthanide complexes interact with a relatively basic pair of electron, an unshared pair of electron. So the shifting that which functional group must be there in order to happen the shifting due to some shift reagent, if you ask, there should be some unshared pair of electron which can coordinate with europium plus 3. Typically aldehydes, ketones, alcohol, thiols, ethers, and amines are interacting. Why do they interact? They have an unshared pair of electron. So when there is an unshared pair of electron, you can use shift reagent. They might be able to do something so that the complex spectra could be simplified. See here, if you see this pair of electron is interacting here, so what happens is like these type of interaction happens. That interaction is reflected in the NMR spectra. So you can the amount of the shift for a given group of proton experiences depends on the distance separating the metal and that of the group of protons and the concentration of the shift reagent in the solution. Hence, it is necessary to include the number of, see, this is a very important point. Hence, it is necessary to include the number of mole equivalents of the shift reagents uses or its molar concentration when reporting the lanthanide shift spectrum. Depends, see, the amount of shift depends on the distance separating the metal and the group of proton. The distance is important, and the concentration of the shift reagent. So the concentration must be, you need to show it when you are expressing the shift. So this is the best example, maybe you may understand. So this is hexanol 1, 2, 3, 4, 5, 6. So hexanol. So in this hexanol, the notable thing is if you take these protons are having a single peak. It's not split. It is single one. So when it is single peak, you can't get information about this 4 different set of protons. So how do you get 4 different set of proton to be split? That's why we use shift reagent. See here, if you observe here, you can see that those protons, each proton is giving different peak just because we were using shift reagent. The proton NMR spectrum of normal hexanol is reproduced in figure 100 megahertz, which is normally recorded. This is 100 megahertz. In the spectrum, the high field triplet is distorted, which represents the absorption of the methyl group adjacent to a CH2 group. The low field broad multiplet, presumably not first order, is due to the methylene group adjacent to the hydroxyl group, all buried in the methylene envelope between 1.2 and 1.8. When the same spectrum is recorded down after the addition of a soluble europium 3 complexes, europium DMP3, this is there, the other I have written small letters. The shift reagent, the spectrum is spread out over a wider range of frequencies so that it is now simplified almost to the first order. In the spectrum down, the OH absorption signal is shifted too far to the observed. So this is the OH peak actually, so it is being shifted to this place. That also to be noted. So hope you understood how the shift reagent works out. And the use of shift reagent in complexes of this type, The lanthanide ion can increase its coordination by bonding interaction with the lone pair electron of group like NH2, OH, CO, ether oxygen, ester oxygens, and cyanide. The magnetic field associated with the metal ion, which is a paramagnetic moiety, causes the marks the change in the observed shift of the proton in the substances. That's why the name shift reagent. What are the advantages of the shift reagent if you ask? It could be advantages of using chemical shift reagents. It could be it gives the spectra which are much easier to interpret. No chemical manipulation of the sample is required with the use of shift reagent, and more easily it could be obtained. You can directly look at the spectra and understand the difference as you did before. The disadvantages are it causes small amount of line broadening at high shift reagent concentration. This problem becomes serious. So generally what happens is we use the concentration of the shift reagent a moderate, but our most useful concentration of the amount broadening is tolerable. Tolerable means it will not make much issue. High field strength. Another technique what we use to simplify the spectra is it has been seen that, so we were discussing about the chemical shift and the coupling constant. If they are comparable, what do we do? Simple. What we have to do is we have to go for high resolution, like you need to increase the field strength. So when the field strength is increased, what will happen? It has been seen that the chemical shift in the hertz is directly proportional to the applied field, but the chemical shift value is independent of the field strength. And the magnitude of the coupling constant is not dependent, or it is independent on the strength of the applied field, but their appearance in the spectrum does not change as the magnetic field changes. So understand the coupling constant will not change with respect to the magnetic field. Whereas the distance, like the splitting, the separation of the chemical shift values increases when you increase the magnetic field. So the one cause of the complexity in proton NMR spectrum relates to the situation where the chemical shift difference between the coupled protons become comparable to the coupling constant. At high field, all the spectra reduces to the simple first order type since the chemical shift difference is far greater than the coupling constant. Thus, for example, AB coupling pattern from these are some terms related to first order spectra. The pattern from the 60 megahertz tends to become an AX type from example a 300 megahertz spectrum, and the signal become easily recognizable and otherwise unresolved signals spread out. So what happens, like if you use high field strength, the chemical shift, if they are comparable, definitely they will become beyond comparable when you go for high field strength. Moreover, too closely spaced signals are also resolved better at larger field strength. So these are the technique that we use to simplify the NMR spectrum. So from this discussion, deuterium labeling and the chemical shift reagents are very important. So thank you.